All right, welcome everybody to Innovative in Education Lecture 3. Today, first thing we're going to do is review some information about orbital combinations and how we combine atomic orbitals and what different types of combinations exist. And then we're going to look at diatomic fluorine as an example of how to sort of implement the LCAO method. And finally, I'm going to close with some discussions of how we build molecular orbitals in bigger organic molecules. And we do that by taking the simple atomic orbitals, the 2s and the 2p, and sort of jumbling them all up together and spitting out orbitals with the correct geometry. And that process is called hybridization. So we'll deal with that at the end of today's lecture. All right, so first, a little bit of review. So the orbital combinations that are allowed are the sigma and pi type combinations. So sigma type combinations involve head-on overlap between two orbitals, right? So we can see in this example the two p orbitals that I've drawn here are overlapping head-on. They're coming directly at one another, and as a result we have what's called sigma type overlap. And let's say that combining these orbitals excuse me, combining these orbitals leads us to one bonding and one anti-bonding orbital with that energy difference between them right there. Pi-type overlap is similar, except the two orbitals are side-on. So this is another example of an allowed combination, but the orbitals aren't pointing directly at one another. Instead, they're parallel to one another as they come towards each other. There is still an interaction there, and it is still favorable in the sense that the bonding orbital is lowered in energy, but it's not quite as extreme as sigma type overlap. So what we would see is the splitting between the bonding and anti-bonding orbitals for pi type overlap is less than the splitting we observe for sigma type overlap. Remember, we label these orbitals with either pi or sigma depending on the type of overlap involved. Finally, we looked at disallowed combinations, which are involved when there's equal parts constructive and destructive overlap as two orbitals combine. So disallowed combinations apply when, for instance, we bring a 2s orbital close to either a 2py or a 2pz. So both of these are perpendicular to the internuclear axis, which would be this axis here. As a result, there's equal parts constructive, which is this interaction of this top lobe with the 2s orbital, and destructive, which is the bottom lobe of the 2p orbital with the 2s orbital overlap as we bring those two together. And so this is a disallowed combination, and we would see no interaction whatsoever because there's no energy incentive for that interaction. Two types of interactions, both of which are allowed, constructive and destructive. So if we add two orbitals together, we take a 2p plus a 2p, we'll get constructive overlap as shown here, and the resulting orbital will have more electron density in between the nuclei than the starting orbitals separated. On the other hand, if we bring two orbitals of opposite phase towards each other, so here we have a dark phase and a light phase coming together, in an instance of a 2p minus 2p combination, what we would see is depleted electron density between the nuclei, like so. And this is an example of a destructive or anti-bonding combination. Again, destructive and constructive overlap are both allowed, but the trick is destructive overlap destabilizes the resulting MO. So for instance, destructive overlap is at work in this anti-bonding orbital here and this one as well, whereas constructive overlap is at work in the bonding orbitals and serves to stabilize those orbitals relative to the separated combinations. So armed with these allowed and disallowed combinations and these ideas, let's take a look at an example of diatomic fluorine. So the Lewis structure of diatomic fluorine is drawn for you here in the upper left and will remain there as we go through this example. You should notice that there are 14 valence electrons in diatomic fluorine, and the atomic orbitals have been drawn out for you down here. Each line represents an orbital, and each arrow represents a single electron present in the AOs of a fluorine atom. So one fluorine atom is represented here on the right and one on the left, and here in the middle we'll build the MO diagram of diatomic fluorine. The orbitals in the middle here will have to contain the 14 electrons that are out on the periphery of the diagram as we build up the combinations. One thing I'll mention here is that we have 8 AOs in. There are 8 atomic orbitals on the periphery of the diagram, 4 for each fluorine, and so we must have 8 molecular orbitals somewhere in the middle of the diagram. 8 AOs in means 8 MOs out, no more and no less when building up a molecular orbital diagram. And that's a law called the law of conservation of orbitals that holds regardless of what molecular orbital diagram you're building. So, for instance, whenever you bring 2 orbitals together, both the constructive and the destructive combination are allowed. So 2 orbitals in and 2 orbitals out, the constructive and destructive combinations. What are the allowed combinations here? Well, to figure that out, we first of all need to know the shapes of the atomic orbitals, right? So the 2s orbital is of course a sphere. The 2px we'll call the bonding axis, the x-axis. So the 2px would look something like this. Oops. Would look something like this. 2py we're going to call the axis coming directly out at us. And so drawing this kind of in 3D as best I can, it would be something like that for the py. Then the pz is going to be just the vertical axis. And so that would be just pointing straight up and down like so. Of course, the same goes for the orbitals over here, px, py, and pz. So what are the allowed combinations? Well, what we want to consider here is to make sure that we're not combining 2 orbitals that are a disallowed combination. So for instance, the 2s with the 2px, the 2py, 2s with the 2py is a classic example of a disallowed combination. So as these 2 orbitals approach along the internuclear axis here, there's equal parts constructive and destructive overlap. So this is an example of a disallowed combination between the 2py and the 2s. Same rule applies for the 2pz. Because the 2pz is perpendicular to the internuclear axis, which we defined as the x-axis, it's an example of a disallowed combination. Any combination between 2 different p orbitals is also disallowed. So the situation with the px is similar to the situation with the 2s. So if we just sub out the 2s for the px, and for instance deal still with 2py, we see that we have equal parts constructive and destructive overlap. So that combination is likewise disallowed. If we take the pz and do the same thing, px with the pz, same deal. So we have equal parts constructive and destructive overlap.